So how does your data navigate a web of nearly a million routes without getting totally lost? Honestly, have you ever actually stopped to think about that? Every single time you send an email or stream a movie or just load a web page, your data has to figure out exactly how to get from your device all the way to a server on the literal other side of the planet. And it does this in milliseconds, cutting through an unbelievably chaotic web of networks. It's wild.
Well, welcome to this explainer. Today, we're going on a little journey into the mechanics of the Border Gateway Protocol, or as we usually call it, BGP. This protocol is, quite literally, the invisible glue holding the entire internet together. So if you've ever wanted to know how the internet actually works at a truly global scale, you are definitely in the right place. To make sure we don't get lost ourselves, here is our very own routing table for today's explainer. We're going to kick things off with the global routing problem, move right into defining autonomous systems, explore the path vector algorithm, break down internal versus external BGP, and finally, look at BGP path attributes. All right, Section 1, the global routing problem. Let's get into it. Okay, let's dive into this. To really understand why BGP even exists in the first place, we have to look at why our standard routing protocols completely fail at a massive scale. Right? In networking, we essentially categorize routing protocols into two distinct camps. On one side, we've got interior gateway protocols, or IGPs. You might have heard of these, things like OSPF or EIGRP. And hey, they're fantastic at their jobs. They're specifically designed to find the absolute fastest physical path inside a single organization's network. But they're strictly internal, strictly local. On the flip side, we have exterior gateway protocols, or EGPs. Now, BGP is actually the only EGP in use today. Its job isn't to route traffic between individual routers in some small office. No, its job is to route traffic between massive corporate networks and global internet service providers. The whole shebang.
And here is exactly why we need a specialized beast of a protocol like BGP. 1 million. That is roughly the number of routes sitting in the global internet routing table right now. That's a lot of routes. Protocols like OSPF simply cannot scale to handle nearly a million routes. Their mathematical calculations would literally melt down standard router processors. BGP, though, it's built specifically to shoulder this unbelievable, massive global load.
Moving right along to Section 2, Autonomous Systems Explained.
You see, there's a huge fundamental misconception about the internet. People think it's just one giant network. Well, actually, scratch that. It isn't. It is actually a collection of thousands of independent networks all stitched together. These independent networks, whether we're talking about your local ISP, a major university, or a massive global corporation, they are called autonomous systems. Now, to play in the big leagues and actually participate in global BGP routing, an organization has to be efficiently recognized as an autonomous system. And they do this by purchasing a globally unique Autonomous System Number, or ASN, directly from IANN, the Internet Assigned Numbers Authority.
And this brilliantly illustrates the concept in the real world, AS 15169. Now, this isn't just some random string of numbers. No way. This is Google's actual public autonomous system number on the public internet. It basically gives a massive network like Google a single unique identity that every other network on the planet can instantly recognize and route traffic toward.
But, it's really important to note that not all ASNs are public. Just like we use private IP addresses for our home Wi-Fi networks, there are private ASNs, and these span from 64.512 all the way up to 65.534. Large enterprises use these internally to manage their own complex routing without broadcasting their private internal architecture to the entire public internet. Makes total sense, right?
Let's check out Section 3, the path vector algorithm.
All right, this is where we learn how BGP actually maps out the internet. And spoiler alert, it doesn't do it the way you probably think it does. Remember those internal protocols we talked about, like OSPF? Well, OSPF is a link state protocol. It looks at the actual physical bandwidth of a cable and calculates a mathematical cost based purely on sheer speed. BGP, on the other hand, is a path vector protocol. BGP honestly doesn't care about the physical speed of a cable at all. Instead, as a route is advertised across the internet, BGP simply attaches a list of every single autonomous system number that the route has passed through. And this running list is what we call the AS path.
So the absolute crucial point here is how this AS path brilliantly solves one of networking's biggest headaches: infinite loops. because the AS path is actually BGP's primary loop prevention mechanism. Imagine a BGP router receives a route update, looks at that running list of ASNs, and suddenly sees its own autonomous system number already sitting right there in the list. It instantly knows, hey, wait a minute, I've already seen this data. This route has basically just gone in a giant circle. So the router immediately drops the update, effectively stopping an infinite routing loop dead in its tracks. I mean, it's incredibly elegant, isn't it?
Let's jump to Section 4, Internal versus External BGP.
Now, what's really interesting here is that BGP actually operates in two very different modes, and it depends entirely on who the router is talking to. If we look at the distinct administrative distances, we can see exactly how routers prioritize these conversations. We have external BGP, or eBGP, which is the connection between two routers in completely different autonomous systems. Imagine your company's edge router talking directly to an AT&T router. eBGP is highly trusted for external routes and uses a low administrative distance of just 20. But then we have internal BGP or IBGP. This happens when two BGP routers are talking inside the exact same autonomous system. Because it's internal, IBGP uses a much higher administrative distance of 200. This clear distinction ensures routers always know exactly where their routing information is coming from, for sure. Now, for any of you out there currently studying for networking certifications like the CCNA, pay attention, because this is vital. Unlike OSPF, which uses multicast to sort of magically auto-discover neighbor routers on a network, BGP requires absolute manual precision. BGP peers do not auto-discover each other. You literally must manually configure BGP neighbors using their exact IP addresses. Once you set that up, they establish a highly reliable TCP connection specifically on port 179 to finally begin exchanging those massive routing tables. There's no auto magic here, just strict rules.
Finally, we arrive at Section 5, BGP Path Attributes. Okay, this is where we learn the real secret of internet routing. Are you ready? It's not just about technology. It's actually about business. Because BGP operates between fiercely competing companies, ISPs, telcos, massive tech giants. It relies heavily on policy-based routing rather than just raw speed. For example, an ISP might configure their BGP routers to force your internet traffic through a specific partner's network simply because they have a cheaper business agreement with them. That means your data might literally take a physically longer path around the entire country, completely bypassing a much faster fiber cable, all because of corporate routing policies. Crazy, right? Let's move along and see how this builds into the actual decision-making process. To enforce all these business agreements, BGP uses a very strict, top-down hierarchy of path attributes to pick the absolute best route. First up, it looks at weight. This is a Cisco proprietary setting local to the router, and the highest weight always wins. Second is local preference. Again, the highest wins, but this one is shared across the entire internal AS. Third, it prefers locally originated routes, meaning routes generated by the router itself rather than learned from somewhere else. And finally, if all else is perfectly equal, it looks at AS path length. It'll just pick the route that traverses the fewest number of autonomous systems. And interestingly enough, that last one, it's actually the most common tiebreaker you'll see out there on the public internet.
So there you have it. We've untangled the massive web of BGP. We've seen how autonomous systems identify themselves, how the path vector algorithm brilliantly prevents endless loops, and how strict path attributes manage the flow of global data based on business rules. So the next time you load a web page, stream a video, or send a message across the globe, I want you to ask yourself, did your data take the absolute fastest path to get you, or just the most profitable one? Thanks so much for joining me on this explainer. Keep learning, and I'll catch you next time.